Hi everyone, I'm Joel Bernstein and I'm going to talk to you a little bit about the research I've been doing with the Resolved Galaxy Survey. Now, the first thing we want to talk about is how we actually classify a galaxy. And the physics that describes the stars and the gas and the dark matter that make up a galaxy could be quite complicated. But broadly speaking, we could talk about a galaxy as being more red or more blue when we look at its color. Now, redder galaxies, they tend to be more elliptical and they tend to have less gas and older stars, whereas bluer galaxies tend to have more gas, and because gas will turn into stars, it'll have newer star formation. And these galaxies also tend to be kind of pancake-like. They tend to be flat, and this is what our Milky Way is. Now, we're also interested in how these galaxies evolve over time. And our models of the universe tell us that galaxies will tend to collide with each other many times throughout their lifetime. So if we have two disk galaxies that collide with each other, you kind of expect that this ordered motion would kind of randomize out as they hit each other and all this stuff goes everywhere. And that would randomize out into something that looks more spherical, more elliptical. You also might expect that this gas might be driven out or it might be all used up in like a rapid burst of star formation. And this might lead to the galaxy looking more red. Therefore, we kind of expect there to not be that many disk galaxies left over time. The problem is when we look at the sky, we actually see that disk-dominated galaxies are going to be the most common type. So this idea that we have, once you get to large enough timescales, it can't actually be a generalization. And one clue that might lead us to where we want to go next is that some elliptical galaxies actually look blue. So if you look at this plot here, we have circles as elliptical galaxies and dashes as spiral galaxies. And as you go to the right, you have more stars. And as you go up, the galaxies look more red. So broadly speaking, you kind of have this red sequence and this blue sequence. But if you look under this dashed line that divides the two, you can actually see that there are some circles here. So if we have some sort of mechanism that lets us transition from a red galaxy to a blue galaxy, this might solve our problem. This leads us to disk regrowth. It's this idea that galaxies, they could actually accrete in gas as a stream from the intergalactic medium. So that's just the stuff, the space in between galaxies. And there's some diffuse gas there. And so if this gets streamed in, it could result in the buildup of a gaseous disk around the elliptical galaxy. More gas will lead to more stars, so obviously this galaxy will look bluer. The physical process kind of associated with this regrowth that we could actually observe would be counter-rotation. Now, if this gas happens to stream in a way that the rotating disk it creates rotates actually opposite to the normal rotation plane of the galaxy, then the stars it forms would do the exact same thing. And then using spectroscopy, we could actually detect this. There are, of course, some problems with detecting this. First of all, it could just be an about 50-50 shot whether it actually streams in the direction we want it to see it, right? Because the gas could easily stream in the same direction as the galaxy rotation plane. And then if we're just looking at the motion of the stars, we'd have no idea that that was as a result of disk regrowth. There's also other factors, such as there could easily be a recent collision, which causes a bunch of anomalous motion in the galaxy. And part of this anomalous motion could easily be part of the disk rotating opposite from the rest of the galaxy. And so we need detailed statistics about the motion of the galaxy itself to kind of suss out the connection between counter-rotation and disk regrowth. And that's what you can see from some work from a previous graduate student down here in this plot. Basically, we just have statistics that are associated with the velocity of the galaxy and radial cutouts. So we want to see what's happening as you go outside. So you kind of have this landscape of what the motion of the galaxy looks like. And that's where my work is going to be focused in the future, is doing some of this work looking at the kinematics.